I know that. Let me try. I'm gonna try one more thing. I'm not gonna be able to hear you guys for 1 second. Just let me see if I can try this. Okay. No, that's gonna be horrible. That's maybe, did I? Oh, wait. Hello. Hello. Bad. Sorry about that. That was probably the worst thing ever. Can I have somebody talk and see if my microphone picks up a separate voice?
Hello.
Do you guys hear that, or is that okay?
That was fine.
Okay, sweet. I'm gonna do it like that then. Okay. We're in business. Whoops. Okay, welcome everybody to another fun round of Biochemistry 1. Glad you all could be here. We're going to be talking about gluconeogenesis. I need to grab one more thing because I started to review all this stuff yesterday, but I've slept since then, so who knows how much I remember. Okie dokie. Starting with the very first question. Adenosine monophosphate will have a blank effect on PFK1 and a blank effect on fructose 1,6-bis phosphatase. Before we answer the question, these two enzymes right here, where do we see those enzymes?
Glycolysis.
In our beautiful, beautiful glycolysis. Glycolysis. That's spelled wrong, but it's fine. There we go. Okay, so if we're looking at this question, what are we thinking as far as the answers go for this question? It's okay, we can guess. There's no points off for guessing.
I think it is going to be inhibiting and then activating. I think.
Okay, so we know, right? Adenosine monophosphate. Adenosine monophosphate, what does that eventually want to become? What are we going to turn that into? I'll give you a hint. There's two other forms. One is a DP, and then there's another one after that.
So ATP?
ATP, right?
Yeah.
So when we create ATP and we use ATP for energy, we actually can strip off and take off two phosphates in order to release energy. So like we have our adenosine right here, and then we have 1, 2, 3 phosphates. So this is our ATP right here. We break off one of these and a whole bunch of energy gets released. And that's what we use to do a lot of our reactions. But we can also, in certain instances, we will also break off this second phosphate off of ADP. And with ADP, then that second phosphate will break off, get released, and then it forms our adenosine monophosphate. So when we have a whole bunch of adenosine monophosphate, what that means is we need energy. Okay? Let me pull up the book really quick. Books. Come on, computer, go, go, go. I also want to double check because while PFK and fructose 1,6-bisphosphatase both do work during glycolysis, I want to double check the whole process of gluconeogenesis and see if we have overlap with those enzymes working in here as well. I can get this to open. There we go. Ooh, which chapter are we in now? Definitely past that. It's chapter like 12, something like that.
14.
14. 11. 12. 13. 14, gluconeogenesis. Let's find out. You gonna kiss me? Okay, here we go. Yeah, so as we can see, so we have glycolysis. Gluconeogenesis is kind of the reverse of glycolysis. We're going to take the opposite steps using those same enzymes, except for these couple specific enzymes like hexokinase, phosphofructokinase 1, and the pyruvate kinase. If we think back and remember these three enzymes specifically, what was special about these three enzymes? What were they called? What were they? They were rate what?
Rate limiting enzymes?
Yeah, there are rate limiting enzymes, right? When we talked about rate limiting enzymes, those ones specifically, remember, those are non-reversible. So once they get pushed forward, and because the reason why they're non-reversible especially is because they are either requiring ATP to be used, or like down here, they're producing that ATP from ADP. So these guys aren't going to be reversible. So what we need is a couple of extra enzymes. So these guys here, and these two down here, to be able to reverse those previously irreversible reactions. Okay? So we have PFK1, our phosphofructokinase 1. So in this case right here, we're talking about we're talking about this one specific step. We're talking about these enzymes on the two opposite sides of the table. So phosphofructokinase, and a little clarification here, I messed this up. PFK is part of glycolysis. the fructose 1,6-bisphosphatase is part of gluconeogenesis. So if we have a whole bunch of AMP, the adenosine monophosphate, we need energy. So in this state where we need energy, do we want glycolysis happening or do we want gluconeogenesis happening? Which of the two is going to give us ATP?
Glycolysis.
Doing the glycolysis, right? So that means we want our PFK1 right here. We want this guy activated. So if we have a bunch of adenosine monophosphate AMP, which means that our ATP has been used up, we're going to activate our PFK1 and inhibit our fructose 1,6-bisphosphatase. So it's going to be C is our answer right there. Because if we need energy, we don't want to be taking, right? We don't want to be taking that pyruvate that we end up with and turning it back into glucose through gluconeogenesis, because we need that pyruvate to go where? Where does it? What's the next step for pyruvate?
To be transformed to acetyl-CoA.
Yeah, and then it goes into that Krebs cycle to get us that NADH and the FADH and that 1-GTP to then go into the electron transport chain to give us all of that ATP within the mitochondria. Any questions or concerns about question 1? Clear as mud in a rainstorm?
Yep.
Perfect. Okay. In humans, gluconeogenesis, I'm going to pause real quick, take a step back. This is where if you don't remember glycolysis super well, I need you guys before you start getting into like your next exam too deep into this stuff. Stop, go back and review glycolysis. Okay, because gluconeogenesis is literally just going to be, at least a good chunk of it, is going to be glycolysis, but in reverse. And just those 3 rate-limiting steps are slightly different. So if you remember glycolysis and you can write all of glycolysis, you know 90% of gluconeogenesis. Okay, so that's going to be the trick, is remembering our glycolysis that we learned before to apply it to gluconeogenesis. Okay, so in humans, gluconeogenesis requires the enzyme pyruvate dehydrogenase, can result in the conversion of protein into blood glucose, is required to convert fats into amino acid, or is required to decrease blood glucose after a carbohydrate meal. Let's go through each answer choice and decide about it. So answer choice A requires the enzyme pyruvate dehydrogenase. Can anybody remember what pyruvate dehydrogenase does?
Catalyzes the reaction to form acetyl-CoA from pyruvate.
Yeah, so it's the step after. We're after glycolysis, right? So pyruvate dehydrogenase is going to work to convert the pyruvates into acetyl-CoA. So in this case, with gluconeogenesis, right, we're trying to go backwards, not forwards. So the pyruvate dehydrogenase will take us forwards rather than backwards. Let's look at D. So D is required to decrease blood glucose after a high carbohydrate meal. What is responsible for decreasing blood glucose after we have a whole bunch of glucose enter our bloodstream?
Insulin.
All right, that's our insulin. Insulin is released from what organ?
Pancreas.
Our pancreas. Specifically in the pancreas, what kind of cells produce insulin?
Beta.
Our beta cells. The beta cells are found in what structures?
Islets of Langerhans.
There we go. Perfect. And insulin, Elizabeth, if you don't give this one, I'm going to be very sad. What's the name of the receptor that insulin binds to?
Tyrosine kinase.
Yeah, perfect. So again, this is, if we look at this, if we have a whole bunch of carbohydrates, we have a whole bunch of glucose in our blood system, there's no need to do gluconeogenesis, right? And now we're down to 2. So let's look at it's required to convert fats into amino acids with gluconeogenesis, right? The job of gluconeogenesis is to produce what?
Glucose.
Yeah, it's to produce glucose. Literally, talking about glucose. Neo is new. Genesis is beginning or create. So create new glucose is its job. Specifically from non-carbohydrate, or from non-glucose sources, right? Better to say non-carbohydrate sources. So not from we're not creating glucose from straight glucose, right? We have something else that's already passed on along the line. Either we can either take from amino acids, we can take from fats, or we can take from other stages of glycolysis, of the Krebs cycle, that kind of stuff, to convert it back and get new glucose. So this question this answer is talking about converting fats into amino acids. And for no reason are we talking about creating amino acids. We don't really care about amino acids. With gluconeogenesis, we're converting the fats, proteins, that other stuff into glucose. So that our answer left is going to be B. It can result in the conversion of protein into blood glucose. Does anybody know, or has anybody been like super into lifting and fitness and dieting, that kind of stuff? Looked into any of that, or know somebody who's super into that? And they talk constantly about how they can't skip a meal. You have to constantly be fueling your body.
Yes.
This is one of the reasons why gluconeogenesis, one of the first places that it actually takes from, is going to be your protein, your muscle storages. So literally, when you don't eat and you don't have enough glucose in your body immediately starts to break down fat and muscle tissue. So that's why, especially with somebody who's like a bodybuilder who's very, very lean already, one of the first places that they start to lose mass is immediately from their muscles if they don't have a consistent source of glucose. So that's why they're eating while working out and like trying to put on muscle is so important, because the second you don't have enough glucose in your system, your body's going to start breaking down other stuff. Sweet. And again, if anybody has questions, stop me, jump in, and we can go back. So question 3, some reaction steps in the glycolytic pathway are bypassed in gluconeogenesis. Which of the following enzymes in the gluconeogenic pathway bypasses one such reaction in glycolysis? We have phosphofructokinase 1, fructose 1,6-phosphatase 1, glucokinase, and pyruvate kinase.
Phosphofructokinase 1. No?
So
Not sure.
Close.
I was going to say the fructose 1,6-phosphatase 1.
It is that this question, it's easy to get confused on this question, because this right here, the phosphofructokinase 1, is the enzyme that it skips. So fructose 1,6-phosphatase is going to skip.
I misunderstood the question. I understand now. Thank you.
The question was a little bit worded weird, because I did the same thing when I first read it. I was like, wait, what? Thinking back, I'm going to test your guys' brains, right? What are the 3 enzymes that we talked about in glycolysis that are our rate limiting enzymes that need to be bypassed in gluconeogenesis? Let's start with there's phosphofructokinase, right? There's PFK1.
Hexokinase?
Yeah, our hexokinase.
And
The very, very, very last enzyme in the whole process.
pyruvate kinase?
And pyruvate kinase, good. Hexokinase gets replaced. It's glucose 6-phosphatase, we talked about last tutoring session. What's the difference between a kinase and a phosphatase? What does a kinase do?
It attaches a phosphoryl group.
Yeah, it attaches that phosphate group. What does a phosphatase do?
Breaks off the.
Yeah, it removes the phosphate. PFK1 is that fructose 1,6 phosphatase, and then pyruvate kinase. We'll get to this again in a little bit. It uses two different enzymes to reverse this step. The first part is pyruvate carboxylase, and then we have PEP carboxykinase. So carboxylase is what a carboxylases do.
Adds a carboxyl group. Yeah. No.
It's going to remove. It removes. It breaks off the carboxyl group, right? And then the kinase. What do kinases do?
Adds phosphate.
Adds the phosphate. Yeah. So we're going to see that a little bit later on. When we get to questions like that, we'll look at that a little bit more. When we get to questions involving that, we'll look at that more. Okay. Bam, fructose 1. Some reaction steps in the glycolytic pathway are bypassed in gluconeogenesis, which are the following enzymes. And the glycolytic pathway is bypassed in gluconeogenesis. Again, this should be a quick one.
Well, the only one there that we just talked about is hexokinase.
Exactly, hexokinase. And what's the enzyme that replaces hexokinase? Actually, first, let's do this. Hexokinase turns glucose into what?
Glucose 6-phosphate.
Glucose 6-phosphate, right? So if we're naming enzymes, right, to go from glucose 6-phosphate back to glucose, what do we need to do? What needs to happen?
Phosphate.
Remove the phosphate, right? So what enzyme removes phosphates?
Phosphatase.
A phosphatase. And what's the phosphatase going to act on?
Glucose 6.
So glucose 6-phosphatase. So if we know glycolysis, we know the process, hopefully we can come up with the name. Good job. The first of the bypass reactions in gluconeogenesis is which of the following? Now, this can be a little bit confusing because we want to remember we've talked about the first reaction in gluconeogenesis. That's the reversing of the last reaction of glycolysis. Does that make sense?
Yes.
Okay. So the very last reaction of glycolysis involves what enzyme?
Pyruvate kinase.
Pyruvate kinase. Sweet. So we're looking here. Pyruvate kinase, we get pyruvate. So immediately when we look at our answer choices, we should be looking for some kind of pyruvate. So answer choice 1, no pyruvate. Oh, there's pyruvate. C, no pyruvate. D, no pyruvate. Only left with B. See, we didn't even have to read the entire question and know all the oxaloacetate and all of this fun stuff. We just needed to know that it's pyruvate. Looking at the other stuff, though. The main one that we want to look at. Let's go. Let's talk about C first. The conversion of fructose 6-phosphate. Actually, no. That's fine. So this reaction, fructose 6-phosphate back to glucose 6-phosphate. This is not a rate limiting step. So it's going to be the same enzyme. Does anybody remember what enzyme does that job? Converts glucose 6-phosphate to fructose 6-phosphate? Or remember what kind of enzyme it is?
Phosphofructoisomerase.
Yeah, our isomerase. Phosphofructose or isomerase, whatever it's called. Our isomerase enzyme is the one that does that. So it's the same enzyme. That one can go, you'll see it drawn as the double-sided arrow. So that one can reverse. It doesn't need a special enzyme to go around it. The conversion of glucose 6-phosphate to glucose. What's the enzyme that does that? Because that is a rate-limiting step.
That one's going to be the glucose 6-phosphatase.
Good. I'm just going to keep drilling these into you guys because like just repetition of it over and over and over again will help you guys remember it way, way easier. Okay. Any questions? If not, moving on. Okie dokie. The first step in gluconeogenesis is which of the following? We did talk about this already. Very briefly, but we talked about it.
Is it the carboxylation reaction?
Yeah, it is a carboxylation reaction. Do you remember the name of the enzyme that we used?
You said there was 2, right?
There is 2. The first one, the first step, though, it's kind of, I don't know if he counts it, if both of the reactions as one step or if he separates them into 2. We'll see if, I think he separates them into 2 steps. Like there's one extra step in gluconeogenesis compared to glycolysis.
So the first one would be starting from pyruvate, which would make it the pyruvate carboxylase.
Yeah. And actually, I think you were right before. The carboxylase is going to add carboxylase. I think you're right. I think you're supposed to add.
I think it pulls it
Yeah.
from a bicarbonate, right? It's from the bicarbonate onto the pyruvate.
Yeah, that's correct. I was thinking a decarboxylase. I got a little confused. Yeah, so carboxylase is the fixation of an inorganic carbon of the CO2. Yeah, my mistake. Carboxylase does add it, it attaches it, it fixes it onto it. The decarboxylase enzymes are going to remove it. So many enzymes. Does anybody remember the second step?
Is the PEP
So
is that a kinase?
Yeah. So literally
Carboxykinase.
the first step attaches that carboxyl group, the CO2 group, and the second step phosphorylates that carboxyl group. So those are the 2 steps. From going in reverse reaction, what does pyruvate then turn back into?
Phospho. It's one I can't pronounce. It's like phosphoenol something or other.
Yeah, phosphoenol pyruvate. Good. This is why we're going to practice our glycolysis forwards and backwards multiple times to figure this out. Sweet. The major site of gluconeogenesis is which of the following tissues? Like 99% of the time, not 99, probably 75% of the time, if we're asking about glucose and where something happens, what should our answer be?
The liver.
The liver. Anytime that we're talking about glucose and like glucose, glycogen, all that sort of stuff, the answer is always going to be either the liver or the muscle tissue. Because we don't store glucose or do any like the other glucose like functions in anything else. It's all up to the liver. This is also why the liver is such an important organ within the body. It's also why, this is a little clinical nugget for you. If you ever hear somebody saying that they have cancer metastasized to the liver. That's like the big one that's just like at that point very, very, very difficult to fight that cancer at that point. So and a lot of cancers will metastasize to the liver because the liver filters all the blood. And so anytime that something detaches off, if you have cancer cells that start to spread, especially through the blood, a lot of times they're going to end up in the liver. So this is a big one. Just a little clinical pearl. If you ever have a situation where cancer is metastasized to the liver, you can automatically assume that it's a pretty advanced stage at that point. And oftentimes, not a lot that can be done medically speaking. Okay. The reaction catalyzed by glucose 6-phosphatase is which of the following? It's irreversible and exergonic, reversible and exergonic, reversible and endergonic, or irreversible and endergonic. Let's break this up into two parts, first of all. Let's say the reaction of glucose 6-phosphatase, right? It's going to be very, very similar to our hexokinase reaction. It's going to be similar, not the same. It's going to be similar. So looking at it like that, is it going to be irreversible or is it going to be a reversible reaction?
Irreversible.
Right, so it's irreversible right out of the gate because we know that same enzyme can't do the job. We have a separate enzyme doing that job, especially also because we need with the hexokinase, we need an ATP to change from glucose to glucose 6-phosphatase, and using ATP releases a whole bunch of energy, right?
Yes.
So our hexokinase reaction is endergonic or exergonic?
Exergonic.
That one is exergonic. And this one, let me double check because I'm seeing the answer and I want to make sure that, because sometimes the answers that he has in here aren't correct, as we learned a couple weeks ago. I just want to make sure. Oh, my bad. I apologize. The ATP itself breaking is exergonic, but the production of glucose to glucose 6-phosphate, this part is exergonic, but this specific reaction with the enzyme is endergonic because it absorbs the energy to form a chemical bond. So, and that's when we talk about the pairing of different reactions. The ATP breaking down is an exergonic reaction paired with the endergonic reaction of hexokinase forming glucose to glucose 6-phosphate. Okay. So this one is endergonic. So then if we're reversing the process and we're breaking the phosphate bond, if we break bonds, what kind of reaction is that? Is that endergonic or exergonic by breaking bonds?
Exergonic.
Exergonic. So our glucose 6-phosphatase is going to be irreversible and exergonic. Right, it's very important to read the whole questions. What is not true about gluconeogenesis? So glucogenic amino acids can be used for glucose synthesis. It requires metabolic energy obtained from ATP or GTP. It uses glucose 6-phosphatase, or it consists entirely of the reactions of glycolysis operating in the reverse direction.
Assuming D because it's not entirely in reverse. Or
Yeah,
well, I
right?
mean, it is, but it's not like the
It's
exact
sort of
same.
in reverse, but it's not the same reactions because we have those different enzymes, those
Yeah.
extra enzymes that we need in order to reverse the irreversible steps. And we know glucose 6-phosphatase is used, metabolic energy obtained from ATP and or GTP. We saw it briefly. Do you remember what step, which of the 3 rate limiting steps uses ATP or GTP?
It would be the first one, right? So from pyruvate to the phosphoenol.
Yeah. So going from pyruvate, using first the pyruvate carboxylase, we get oxaloacetate, and then using the PEP carboxykinase, and we use 2-GTP to go back to phosphoenol pyruvate. So we're literally using 2-GTP and 2-ATP to go from pyruvate to phosphoenol pyruvate. And then glucogenic amino acids can be used for glucose synthesis, and that is correct. So the glucogenic amino acids, I don't think he asks specifically like which amino acids they are. If he does later on, I'm sure we'll see that, and then we can touch on those. What is the coenzyme for the pyruvate carboxylase enzyme that produces oxaloacetate? First important question we have are 2 things that we use that are used as an association with our enzymes. We have cofactors and coenzymes. Coenzymes and cofactors, what are they? Not like specifically, but in general.
Cofactors are like magnesium, like minerals.
Yeah, there are minerals that are metals. So magnesium, copper, iron, sodium, potassium, calcium, all of those guys, like sodium, potassium, calcium, those are like a soft metals. So all of the cofactors are our metals that are involved. And what are our coenzymes?
Vitamins.
Our vitamins. So immediately, if we look here to the left, if we know that a coenzyme is going to be a vitamin, of these 4, which are vitamins?
Biotin.
So biotin is a vitamin. And there's one more.
The pyridoxal phosphate.
Pyridoxal phosphate. So we have adenosine is not adenosine. What is adenosine? An amino acid. And then inorganic phosphate is just a molecule. Okay. So between the 2, pyridoxal phosphate and then biotin. This is something, let me pull up. I have a pretty little chart. The chart that I'm going to pull up has a lot of the vitamins. You don't need to know all of this information right now. It is part 1 boards. There's a lot of this stuff on there. See if this will open up. Takes a sec. Bling, bong, bong, bling, bong, bong, bling, bong, bong. No. Does anybody remember the mnemonic that I've talked about? To remember all of, well, I guess biotin and pyridoxal phosphate are both B vitamins. Do you remember the mnemonic to remember all of the B vitamins?
Oh, hang on. I had it. Oh. Oh, it's
Tall,
gone.
rich, nudists, played pickleball for centuries. This is B1, B2, B3, 5, 6, 7, 9, and 12. Highly, highly, highly recommend you remember the B vitamins, because you will have a crap ton of questions on B vitamins in, I think there's a chunk in Biochem too that you get questions about vitamins. Then a whole bunch in clinical nutrition, which is try 5, I believe, try 4 or try 5. You also have questions about B vitamins a lot on boards. They like B vitamin questions on boards. You'll have it both in the biochemistry section as well as the general diagnosis question, as well as the pathology portion, because each of these B vitamins, a deficiency in the B vitamins, correlates to specific symptoms of disease. So you'll see it in both. You'll also need this. You'll see a lot of B vitamin deficiencies in systems pathology, which is try 4, and what's the name of that other class? Physical diagnosis in try 4 as well. So you'll want to know your B vitamins. So here's our beautiful B vitamin chart. So we look at B1, decarboxylation reactions, B2, oxidation and dehydrogenase, B3, oxygen and dehydrogenase. That's our NADH and our FAD, those guys. So that's our oxidation reduction, also the dehydrogenation. Pantothenic acid is part of coenzyme A. Pyridoxine or pyridoxal phosphate, which is seen in this question that we just got asked, is used for transamination and for amino acid metabolism. And then our beautiful biotin, also known as biocytin in its active form, but biotin, B7, does our carboxylation, for example, acetyl-CoA carboxylase, for these types of reactions. So if we look, our pyruvate carboxylase, our answer is going to be biotin. He could also put as an answer choice B7 instead of biotin, or he could also put biocytin. More than likely, though, he'll stick to either biotin or B7. Those are the main two that you'll see. But he could ask it. It could have either of those as an answer choice. Any questions about that?
It helps when you go through it. Thank you.
Yeah. Just to round it out, you'll also see later on, you'll talk a ton about B9 and B12. Like a ton about B9 and B12. B9 and B12, this is not so much for this class right now. This is going to be for future. B9 and B12. B9 specifically is responsible for most of the birth defects that you'll see, especially in the early stages of pregnancy. So like spina bifida, the neural tube defects. A lot of times, like if you have a fetal demise due to like things not forming correctly, very, very often it's because of B9 vitamin deficiency. That's why when you get pregnant, or even before you get pregnant, almost every single OBGYN is going to tell you to take a supplement specifically with folate, folic acid, tetrahydrofolate, one of those in there, B9, specifically when you're trying to get pregnant or when you are pregnant. So B9 and B12 are also very, very responsible for anemia. And all of our B vitamins are found within animal products. So these guys, especially B12, people who don't eat animal products, you'll see a lot of the times when they start to get sick or they have issues, a lot of times you'll see autoimmune conditions with vegetarian and vegans, specifically if they are vegetarian and vegan and they're not properly maintaining their diet or supplementing with their diet. So you'll talk a lot more about that in future trimesters, but just a little introduction here to it all. And this stuff is also really, really important to remember. A little experience. I had a patient come in, this was last trimester, who was having numbness, tingling and stuff, kind of like neuropathy type symptoms in both of her legs. And you can have that. One of the causes of that are B vitamin deficiencies, which you see a lot in the geriatric population, a little bit older, the senior population, because their stomach acid becomes less acidic, less potent. And so your body actually can't break down and absorb the B vitamins from proteins like they're supposed to. So lots of little clinical pearls today. Continuing, so which of the following compounds can be used as the starting material for gluconeogenesis?
All of the above?
Yeah, the answer is all of the above. He doesn't have the nice little chart. Does anybody remember there was a chart where it kind of looks like this? It has like a circle here and then it branches off and you have stuff coming in and stuff going out. There's a chart like that. Let me see if I can find it. It was way earlier in the book. I don't want to go back to the book to find it, but I have to go back through the book and find it. It was way back there, though. See if I can.
I think it was in
Find
the citric acid cycle.
Yeah. Somewhere in
like 138 or something like that.
Kind of like this. There was another one similar to this. Let's see. I need to find it because it's a really, really, really good one. And it was at like the very end of a unit. Might have been the amino acids. To find it. Dang. I know it's in his slides somewhere, but essentially what it does is it shows all of the different places that the different amino acids can convert to different stages within the Krebs cycle. And along with that, it also has arrows pointing out saying that such and such material can go to gluconeogenesis and produce glucose. I know it's in here somewhere because every time I get to it, I circle it. This guy. Here we go. Oh, you were right. You're right. I was looking at PDF number, not page number. Yeah. Page 138 in the book. So this kind of stuff. It might be in his slides where he specifically says, kind of the direction that they go. But yeah, this PE right here, this PEP carboxykinase. right there. That's the same enzyme we talked about. Converting the phosphoenol pyruvate back to oxaloacetate, or oxaloacetate going the opposite way in the PEB carboxylase. So these enzymes that we talked about with gluconeogenesis. So it's a good chunk of these different amino acids. Again, like I said, I don't think he specifically asks about the amino acids, like which amino acids convert, but I don't think he does in this trimester. I feel like this comes back, if I remember correctly, in Biochem 2. It's been a little while since I've gone through the entire Biochem 2 book. But I want to say that this comes back later on. So all of these, the fumarate, pyruvate, malate, basically anything close to oxaloacetate can go backwards because we see oxaloacetate formed in that very first step of gluconeogenesis. So which of the following compounds cannot be used as a precursor for the synthesis of glucose via gluconeogenesis? This one, and it's going to be bicarbonate. The rest of these, pyruvate, alanine, and glycerol, are all similar enough in different ways to be able to get them through the processes to turn into some form of either some form of an intermediate within the Krebs cycle or within glycolysis to let it go backwards for gluconeogenesis. Oops. Which of the following conditions stimulates gluconeogenesis? A very low carbohydrate diet, extensive exercise, or starvation? Basically, the question is saying, in which of these conditions do we need to make more glucose?
All of them.
Yeah,
Yeah.
all, I guess.
All of the above. Because if we're starving, right? Starvation, we talked about this. If we don't eat for a while, our body starts to break down our muscle tissue, or uses up our fat storages. Or has anybody ever watched the show Survivor?
Yes.
So you see, they always do a body reveal where how much weight each contestant lost and that kind of stuff as they were going through Survivor. And that's because they're literally putting themselves into a starvation state. And so their body's going to start breaking down fat and muscle and everything else to create glucose. Again, if we have a very low carbohydrate diet, very, very common, like the Atkins and the keto diets are very, very low carbohydrate diet. Again, not on your test, but if at any point any of you get a traumatic brain injury or a concussion, the keto diet is best for brain recovery. Not necessarily long term, but having a keto diet after a TBI or concussion, very, very good, very, very helpful for brain recovery.
Yes,
So it's happened it's happened a couple of times to students around in the area or students at Parker where they get a concussion and they don't give you a ton of time for returning back to campus. So if you do get a concussion, high protein, high fat, very, very low carbohydrate diet for about a week is very, very helpful in kind of getting your brain to recover, to heal, to do its thing. Which of the following energy molecule is used by the phosphoenol pyruvate, aka that PEP carboxykinase enzyme? Now, first of all, is this step 1 or is this step 2?
This is the second one.
Yeah, this is step 2. So are we using AMP, ATP, GTP, or acetyl-CoA?
GTP.
Yeah, we're going to be using GTP. ATP we use in step 1. AMP, if that's present and we're doing glycolysis. Acetyl-CoA, that's a continuation of glycolysis into the Krebs cycle. Good job. Which of the following enzyme catalyzed reactions in gluconeogenesis bypasses hexokinase catalyzed reaction in glycolysis? Kind of a repeat question that we've had from before.
It's the glucose 6 phosphatase, right?
That is correct. Glucokinase is found in what tissue?
Muscles and liver.
Liver?
Glucokinase is found in the liver only.
Only crap. Okay.
Hexokinase is found in all the tissue, in the muscle and in the liver. Which of the following enzymes is used in both glycolysis and gluconeogenesis? So if it's used in both, does that mean that enzyme is a rate limiting step or a non-rate limiting step enzyme?
Non-rate limiting.
Non. So immediately we look here. Rate limiting, rate limiting, rate limiting step. And all we're left is our 3-phosphoglycerate kinase. Which again, I didn't have to know every single step of glycolysis to answer that question, because I knew exactly which ones were the 3 rate limiting steps and what had replaced them. Which of the following enzymes is /R used in both glycolysis and gluconeogenesis?
All of them?
The answer correct. The answer is all of them. This is another question where if you don't remember every single thing that goes on in glycolysis, get out your little flashcards or whatever you used to memorize glycolysis the first time you took the test and start reviewing them again, because you're going to want to remember glycolysis to remember gluconeogenesis. Which of the following enzymes produces oxaloacetate in the gluconeogenic pathway? So remember, we go from pyruvate to oxaloacetate to our whatever is a phosphopheno enol pyruvate, whatever it's called. Phosphoenol pyruvate. What is the enzyme? Right here in the very first step of gluconeogenesis.
Pyruvate carboxylase.
Yeah, because we add the carboxyl group and then we add the kinase. So this is step 1, and here is step 2 of gluconeogenesis. What does citrate synthase do?
Form citrate from oxaloacetate and acetyl coenzyme A.
Yeah, good job. I'm gonna keep bringing that stuff back just because the final don't know exactly what kind of questions he'll put on there. Which of the following events occurs during the synthesis of phosphoenol pyruvate from pyruvate during gluconeogenesis? So we're going from pyruvate to phosphoenol pyruvate. Which event occurs? Inorganic phosphate is consumed, ATP is synthesized, CO2 is consumed, or acetyl-CoA is used. Starting from here from the bottom, do we ever talk about using acetyl-CoA?
No.
No. Boom, 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 boom. ATP is synthesized. Are we synthesizing ATP or are we breaking down ATP?
Breaking it down.
What else are we breaking down?
Bicarbonate.
But bicarbonate. What's else similar to ATP? What about in the second step of gluconeogenesis?
GTP.
First step is ATP. What's in the second step?
GTP.
Yeah, or GTP. This question, I don't love. I kind of question if this is the correct answer. He has that the correct answer is A, that an inorganic phosphate is consumed. However, I would kind of question that one. Just because all of the graphs and everything don't really talk about an inorganic phosphate. They do mention the CO2. This is a question for Dr. Sarkar, just to make sure that this is actually keyed correctly. Like I said, because I would kind of question this one here, unless there's something
I think
deeper
the hint,
that I don't know.
I think the hint there is that CO2 is produced during that, but not necessarily consumed.
Well, and the only other thing I was thinking was, would it be because as you break down the ATP to ADP, then it's consuming the extra phosphate there?
I would think so. That's probably what he's getting to. But also the CO2, because you have a carboxylase, the carboxylase attaches the CO2 to the pyruvate to make oxaloacetate. I think with this one, what I might be a little confused on is maybe what the definition of consumed means. So I would ask Dr. Sarkar about this to confirm. I could see either of these answer choices being correct. I just don't know exactly kind of as far as like the biochemical exact definition, what consumed technically means. So if it's in his book like this, I would say if this exact question pops up, go with answer choice A. If it gets marked as wrong for whatever reason, come back and go meet with him and show him like, hey, well, in the book, it said that this is the correct answer. Here's why I think why. I also thought that was a potential answer. Here's why. And you should be safe in doing both of those things. So that's what I would say with that. I don't love that question. Okay. Which of the following pair of enzymes in gluconeogenesis bypasses the pyruvate kinase reaction as seen in glycolysis? Hopefully this should be second nature answering this question at this point. What do you think? A, B, C,
Having 3
or
screens
D?
is suck. It's C.
It's
So-
C, yeah.
My
Immediately,
cursor's
because
all the
immediately we
way
can
on
look
the
at so
left.
there's a pyruvate there. That's no pyruvate. That's whatever. Pyruvate carboxylase, phosphorus kinase, not that one. Right there. Not supposed to be a space there. But yeah. Hopefully I'll never forget these enzymes, because I don't think I ever will. This is like the 4th time I've done this, so I taught this stuff, material in general, so I've seen these enzymes a lot. Which of the following processes is energetically more expensive? Anaerobic oxidation of pyruvate, glycolysis, conversion of glucose to glucose 6-phosphate, or gluconeogenesis.
I'm gonna say gluconeogenesis just because that's what we're in, but I don't really understand what he's asking.
So when he says energetically more expensive, kind of like how like glycolysis, you have to use 2 ATP. You have to put in the energy in order to produce all this stuff. This is another one that says he has the answer keyed as glycolysis. However, I would say this is going to be another one that I want to ask him because he has the answer as glycolysis. However, gluconeogenesis uses 2 ATP and 2 GTP and has 0 production of ATP, whereas glycolysis uses 2 ATP but produces 4 ATP, thus netting positive 2 ATP. So I would think the answer is supposed to be gluconeogenesis, unless there's some deeper voodoo that, you know, is involved with getting a PhD in biochemistry like Dr. Sarkar has, that isn't super obvious on the surface level of reading the textbook and going through everything. My guess would be that this is keyed wrong. So I personally, this is one either you need to talk to Dr. Sarkar about it. Personally, I would put gluconeogenesis and be able to defend my answer with glycolysis. You get 2 ATP, whereas gluconeogenesis, you're losing 2 ATP and 2 GTP for a net loss of 4. So,
and I just looked at my quiz because I took the quiz for this week, and it did ask me that question, and the correct answer was gluconeogenesis on the quiz.
Okay, there we go.
I will also go into that Quizlet that I sent you, Drake, and make sure that I change it because I'm pretty sure I just copied whatever he had keyed. So that's when I'll go in and I'll change.
Yeah, so we saw that there's a handful of these that, you know, are a little bit off. So, yeah, kind of like this one. Like I guess I don't love this question either, just because both of these answers could be correct. I would probably put that in there as well as just as biggest thing is understanding why they're both correct. So that way, if you have to defend your answer at any point, you can do it appropriately, and hopefully gets points back. Our last question: which of the following statements about gluconeogenesis is not true? It uses glucose 6-phosphatase. Please, for the love of everything, we've talked about that enzyme 8 million times at this point. That is true. It consists entirely of the reactions of glycolysis operating in the reverse direction. If I'm not mistaken, we've actually had this exact same question already once. And that is not true. It is not just the same reactions in reverse because we need to skip those rate-limiting steps. It requires metabolic energy obtained from ATP and or GTP. That is correct. And glucogenic amino acids can be used for glucose synthesis, and we know that that is true. Sweet. So gluconeogenesis. How do we feel about gluconeogenesis? Not too bad, right?
Not so bad.
Yeah, it's not too bad as long as I remember glycolysis.
Yeah, go back, review glycolysis. And I would also personally recommend, this is kind of a long-term if you're prepping for boards kind of thing. Stuff like glycolysis, the Krebs cycle, electron transport chain, those kind of things. Every so often, kind of set a reminder for yourself on your phone or something that like every 3-4 weeks or so, like come back to those and just run through them a time or two. Because that's the kind of stuff that when you get to boards, preparing for boards, it's just pure raw memorization type stuff. And you don't want to be prepping for boards just doing raw memorization BS. Like it sucks. So if you can come in and remember a lot of this stuff, boards will be a lot easier. And honestly, I would probably use a lot of the questions that he has in this Linus stuff. I would use these as board study material. I think they're fantastic for that. And practicing a lot of the stuff with these questions. So, okie dokie. Any other questions, comments, concerns?
You're awesome. Thank you.
Thank you guys for being here. Appreciate it. I think, let me check my, oh, I might have just broke my phone. No, we're good. Let me see. I'm planning on doing another session on Thursday. Let me see. That's 2 o'clock. It'll be in the afternoon, probably. Right now I have it set to be around 2:30 start time. So, do you guys have another test this Thursday?
We have DAA.
Gross. Tell your teachers to stop putting tests on Thursdays. I guess it's better than Fridays.
Very much so.
But yeah, and with that, I guess if we're caught up right now, I guess we'll continue to jump ahead and push forward a little bit more with more material. And again, if you have any questions, concerns, or anything before then, feel free to shoot me a message and ask. Also, I guess I'm gonna end the recording right here real quick. How are all the rest